An old idea. Revived, starve. Cancer to death. The story of modern cancer research begins, somewhat improbably, with the sea urchin. In the first decade of the 20th century, the German biologist Theodor Boveri discovered that if he fertilized sea urchin eggs with 2 sperm rather than 1, some of the cells would end up with a wrong number of chromosomes and fail to develop properly. It was the era before modern genetics, but Boveri was aware that cancer cells, like the deformed sea urchin cells, had abnormal chromosomes. Whatever caused cancer, he surmised, had something to do with chromosomes. Today Boveri is celebrated for discovering the origins of cancer, but another German scientist, Otto Warburg, was studying sea urchin eggs around the same time as Boveri. His research, too, was hailed as a major breakthrough in our understanding of cancer. But in the following decades, Warburg's discovery would largely disappear from the cancer narrative, his contributions considered so negligible that they were left out of textbooks altogether. Unlike Boveri, Warburg wasn't interested in the chromosomes of sea urchin eggs. Rather, Warburg was focused on energy, specifically on how the eggs fueled their growth. By the time Warburg turned his attention from sea urchin cells to the cells of a rat tumor, in 1923, he knew that sea urchin eggs increased their oxygen consumption significantly as they grew, so he expected to see a similar need for extra oxygen in the rat tumor. Instead, the cancer cells fueled their growth by swallowing up enormous amounts of glucose, blood sugar, and breaking it down without oxygen. The result made no sense. Oxygen-fueled reactions are a much more efficient way of turning food into energy, and there was plenty of oxygen available for the cancer cells to use. But when Warburg tested additional tumors, including ones from humans, he saw the same effect every time. The cancer cells were ravenous for glucose. Warburg's discovery, later named the Warburg effect, is estimated to occur in up to 80% of cancers. It is so fundamental to most cancers that a positron emission tomography (PET) scan, which has emerged as an important tool in the staging and diagnosis of cancer, works simply by revealing the places in the body where cells are consuming extra glucose. In many cases, the more glucose a tumor consumes, the worse a patient's prognosis. In the years following his breakthrough, Warburg became convinced that the Warburg effect occurs because cells are unable to use oxygen properly and that this damaged respiration is, in effect, the starting point of cancer. Well into the 1950s, this theory, which Warburg believed in until his death in 1970 but never proved, remained an important subject of debate within the field. And then, more quickly than anyone could have anticipated, the debate ended. In 1953, James Watson and Francis Crick pieced together the structure of the DNA molecule and set the stage for the triumph of molecular biology's gene-centered approach to cancer. In the following decades, scientists came to regard cancer as a disease governed by mutated genes, which drive cells into a state of relentless division and proliferation. The metabolic catalysts that Warburg spent his career analyzing began to be referred to as housekeeping enzymes, necessary to keep a cell going but largely irrelevant to the deeper story of cancer. It was a stampede, says Thomas Seyfried, a biologist at Boston College, of the move to molecular biology. Warburg was dropped like a hot potato. There was every reason to think that Warburg would remain at best a footnote in the history of cancer research. As Dominic D'Agostino, an associate professor at the University of South Florida Morsani College of Medicine, told me, the book that my students have to use for their cancer biology course has no mention of cancer metabolism, but over the past decade, and the past 5 years in particular, something unexpected happened. Those housekeeping enzymes have again become one of the most promising areas of cancer research. Scientists now wonder if metabolism could prove to be the long-sought Achilles heel of cancer, a common weak point in a disease that manifests itself in so many different forms. There are typically many mutations in a single cancer. But there are a limited number of ways that the body can produce energy and support rapid growth. Cancer cells rely on these fuels in a way that healthy cells don't. The hope of scientists at the forefront of the Warburg revival is that they will be able to slow, or even stop, tumors by disrupting one or more of the many chemical reactions a cell uses to proliferate, and, in the process, starve cancer cells of the nutrients they desperately need to grow. Even James Watson, one of the fathers of molecular biology, is convinced that targeting metabolism is a more promising avenue in current cancer research than gene-centered approaches. At his office at the Cold Spring Harbor Laboratory in Long Island, Watson, 88, sat beneath one of the original sketches of the DNA molecule and told me that locating the genes that cause cancer has been remarkably unhelpful. The belief that sequencing your DNA is going to extend your life a cruel illusion. If he were going into cancer research today, Watson said, he would study biochemistry rather than molecular biology. I never thought, until about 2 months ago, I'd ever have to learn the Krebs cycle, he said, referring to the reactions, familiar to most high school biology students, by which a cell powers itself. Now I realize I have to. Born in 1883 into the illustrious Warburg family, Otto Warburg was raised to be a science prodigy. His father, Emil, was one of Germany's leading physicists, and many of the world's greatest physicists and chemists, including Albert Einstein and Max Planck, were friends of the family. When Warburg enlisted in the military during World War I, Einstein sent him a letter urging him to come home for the sake of science. Those men had explained the mysteries of the universe with a handful of fundamental laws, and the young Warburg came to believe he could bring that same elegant simplicity and clarity to the workings of life. Long before his death, Warburg was considered perhaps the greatest biochemist of the 20th century, a man whose research was vital to our understanding not only of cancer but also of respiration and photosynthesis. In 1931 he won the Nobel Prize for his work on respiration, and he was considered for the award on 2 other occasions, each time for a different discovery. Records indicate that he would have won in 1944, had the Nazis not forbidden the acceptance of the Nobel by German citizens. That Warburg was able to live in Germany and continue his research throughout World War II, despite having Jewish ancestry and most likely being gay, speaks to the German obsession with cancer in the first half of the 20th century. At the time, cancer was more prevalent in Germany than in almost any other nation. According to the Stanford historian Robert Proctor, by the 1920s Germany's escalating cancer rates had become a major scandal. A number of top Nazis, including Hitler, are believed to have harbored a particular dread of the disease. Hitler and Joseph Goebbels took the time to discuss new advances in cancer research in the hours leading up to the Nazi invasion of the Soviet Union. Whether Hitler was personally aware of Warburg's research is unknown, but one of Warburg's former colleagues wrote that several sources told him that Hitler's entourage became convinced that Warburg was the only scientist who offered a serious hope of producing a cure for cancer one day. Although many Jewish scientists fled Germany during the 1930s, Warburg chose to remain. According to his biographer, the Nobel Prize-winning biochemist Hans Krebs, who worked in Warburg's lab, science was the dominant emotion of Warburg's adult life, virtually subjugating all other emotions. In Krebs's telling, Warburg spent years building a small team of specially trained technicians who knew how to run his experiments, and he feared that his mission to defeat cancer would be set back significantly if he had to start over. But after the war, Warburg fired all the technicians, suspecting that they had reported his criticisms of the Third Reich to the Gestapo. Warburg's reckless decision to stay in Nazi Germany most likely came down to his astonishing ego. Upon learning he had won the Nobel Prize, Warburg's response was, "It's high time." Modesty was not a virtue of Otto Warburg, says George Klein, a 90-year-old cancer researcher at the Karolinska Institute in Sweden. As a young man, Klein was asked to send cancer cells to Warburg's lab. A number of years later, Klein's boss approached Warburg for a recommendation on Klein's behalf. George Klein has made a very important contribution to cancer research, Warburg wrote. He has sent me the cells with which I have solved the cancer problem. Klein also recalls the lecture Warburg gave in Stockholm in 1950 at the 50th anniversary of the Nobel Prize. Warburg drew 4 diagrams on a blackboard explaining the Warburg effect, and then told the members of the audience that they represented all that they needed to know about the biochemistry of cancer.